All right, this is a challenge problem and a real-world connection problem in our work with quadratic functions, and specifically under the topic of quadratic functions where our b value is 0. So we're just looking at ax squared plus c equals y. So we'll do a couple, and I encourage you to pause this video and try these on your own, and then check back in and see how you did. So pause on this guy and you can see what it is, and then I'll scroll down. This is the second one we'll be doing, so I really want you to try these on your own and then check back in. So for the first one, a little bit more abstract, we're starting with the parent function y equals x squared, our core fundamental parabola, and then we're applying some transformations in different orders. So for the first one, first I want us to stretch it by a factor of 2 and then do a vertical translation of -3. And then in the second one, we're going to flip the order. So first we'll do the vertical translation of -3, and then we'll stretch it by a factor of 2, and we'll see if anything's different. Okay, so first what I want to do is just get in our core parent function down here as f of x. So these are just going to be the x values squared. Okay, and then in the second one, we'll do that first transformation. Okay, so this is just x squared right here. So we're going to double it and then subtract 3. So 47, and we have symmetry to help us here, be a little more efficient. 16 double is 32, minus 3 is 29. 5 and 5, 1 doubled is 2, minus 3 is -1, and that's going to be a, let me think, a -3 here. Okay, so we have a set of values. We could plot them. We're not going to right now, but we could. And so we have a parabola that's been vertically stretched and then shifted down. For the second one, let's flip the order of the transformations. And I guess we're mostly curious, are we going to get the same thing? So we are going to go from our parent function to here doing the transformations. So first we'll subtract 3 to get 22 and then double it to get 44. So I think you can see that already that we're getting a different outcome. And so maybe as I go through these numbers, look for a pattern, see if you notice a connection between the f1 numbers and the f2 numbers. 16 minus 3 is 13, doubled is 26. 12, 4 minus 3 is 1, doubled is 2. 1 minus 3 is -2, doubled is -4. And then 0 minus 3 is -3, doubled is -6. All right, do you see a pattern? It looks like, and just to be specific, just to be clear here, we're looking for a pattern between our f1 values and our f2 values, okay? So those are the results of doing the same transformation but in a different order. It looks like they're all off by 3, right? f2 is always 3 less than f1. So let's see if we can figure out why that is. So f1 of x, we started with our x squared, we doubled it, that's multiplied by 2, and then we subtracted 3. Let's think about what we did for f2 of x. Again, we started off with our x squared, but here we subtracted 3, and then we doubled the entirety of that. Okay, and so we can do the distributive property and get 2x squared minus 6 is equal to f2. So I think you can see here f2 versus f1, why they differ by 3 because of these two values right there. One we're subtracting 3 at the end, and one we're subtracting 6 at the end. All right, maybe go ahead and try to graph those two on Desmos or by hand if you want also. Next one we'll do is a little bit of a real-world connection problem, and the scenario is this. Don't ever do this scenario in the real world though, okay? I drop a watermelon off of a 25-story building. Under Earth's gravity, the height of a dropped object from an initial height of s feet can be modeled by the quadratic function. h of t equals -16 t squared plus s. So we're going to use Desmos to graph the function and estimate the time it takes for the watermelon to hit the ground. Okay, so let's just be clear about what our variables are. S is where we're going to plug in our height. That's our initial height, okay? And it looks like we'll need to use this information along with the fact that it's a 25-story building. t is our independent variable. That's time. So as time goes by, the height of this watermelon changes. Okay? And h of t is our dependent variable. That's what we're trying to figure out. That's the outcome of this function. Gives us the height of the watermelon at any particular time. However, in this case, we're wondering how long it'll take the watermelon to hit the ground. So what that means is h of t is going to be 0. T, we don't know what it's going to be. That's what we're going to solve for. And s, it looks like, is going to be 250. 25 stories, 10 feet for each story. Okay, hopefully that makes sense where we got those things, and we're looking at solving for t here. Okay, so let's go ahead and graph it up on Desmos. So we have h of t. Remember, you can just always plug in a y instead of function notation. Desmos can take either. Negative 16 x squared plus 250. So just to be clear here, just to make sure you're totally clear on this, I also could have done h of t equals negative 16 t squared plus 250. Same thing, okay? So let's go ahead and actually do the formal function notation like we were looking for. So Desmos is telling us what the height is at various times. So for example, right there, after about 2.5 seconds, our watermelon is still about 150 feet off the ground, okay? Also, to be clear, this parabola doesn't model the physical track of the watermelon. The watermelon's being dropped straight down, okay? This parabola models a graph of the height of the watermelon versus time. So time is the x-axis. So this isn't showing the physical track of the watermelon. And we can figure out when's that watermelon going to hit the ground. It looks like it reaches a height of 0 at about 3.95 seconds. So we can go back and get our answer written in. Let's actually type in what we did. We did 0 equals negative 16 t squared plus 250. So t is roughly 3.95 seconds. That's about how long it takes that watermelon to hit the ground. All right, good place to stop right there.